And thanks, Chris. That was great. And you know, it's funny. It's because it's my first time here, but I have so many old friends here. It feels like, yeah, it's like old home week. So it's nice. And I hope this does, I mean, from conversations today, which have been really great, and I hope they continue and, you know, will be enhanced with some kind of alcohol later, that, you know, like this does sort of fit in a couple of people's wheelhouse here. And, you know, it'll be fun. This is the first time I'm presenting, well, I presented some of these data elsewhere, but it's really the first time I'm giving this talk, and so I want it to be really open-ended. If there's something that's confusing or something occurs to you, like, have you tried this? Go ahead and raise your hand in the middle, and we'll, because, you know, I can't talk for an hour and a half straight. Well, I can, I guess. I do it for a living, but I don't want to necessarily. So the title is Statistical Learning of Auditory Patterns as Trajectories Through a Perceptually Defined Similarity Space. And so I'll just break that down. I guess I'll start by breaking that down. Right, there's this idea of, which many of you are familiar with, that statistical learning is an important component of learning language, right? So here's a simple recurrent network, right? Most of you I hope all of you have encountered some version of this at a time, right? The SRN's job is to predict what's going to happen next, given the current input and a copy of its internal state from the last thing that it encountered, right? And simple recurrent networks can have all sorts of nice properties if you feed them an undifferentiated set of letters, so you have words written, but they're strung together so that there are no spaces. The model can find where there ought to be spaces based essentially on the transitional probabilities of the letters from one to the other. So, you know, you have this many years ago, a boy and a girl, etc., right? And those troughs there are like where the error function is, where the error function is the lowest. That is, it can best predict what's coming up because that's the most likely conclusion to those words. And then the peaks in the error there are where new words begin, right? So that's exciting because we didn't tell it anything about English words. We just gave it, you know, essentially sequences, and it figured out how to parse those sequences into some kind of meaningful chunks. And, you know, I mean, you know, Jeff had to probably pick some sentences so that it would work just like this because there's tons more ambiguity than is evident here, but like it does something interesting and worthwhile, right? And you can even push this if you do this now at the word level rather than at the letter level. You can show that you develop a sort of similarity space that incorporates some aspects of syntax and semantics together based on the co-occurrences, the likely co-occurrences of words, right? So so there's a demonstration here that, you know, structure at multiple levels can be learned by this simple algorithm, right? Predict x at t from x at t minus 1. And the accumulated context of all the prior x's, right? So your existing state is the result of your prior experience, and then you get a new thing, and you can predict the next thing by some combination of the input and how you're representing what just happened to you. And the radical proposal, right? The exciting thing, and the reason people got really angry about these demonstrations was, you know, there was this radical proposal. Well, what if language is learnable without any domain-specific assumptions about its structure? What if you can just do this, right? You can just absorb these statistics, and then you can learn all kinds of stuff that you need to know about language. So does anything like this really happen? Like, for real, though? That's what I said, that's what I wrote there, right? So, and like, you know, so there, like Peter Jusek had been working on word segmentation and showing that different sorts of cues are relevant for word segmentation, a lot of them related to prosody and words appearing by themselves. But there was a really sort of, well, I have so many metaphors in my head for what this paper was. It's like the thing that broke the dam open for these studies was the Safran et al. Study in 1996, where you heard where infants heard monotone sort of recitations of syllables that were strung together. And so it would be like to, ki, bu. I'll play you something like this in a second, but like to, ki, bu, ki, ko, ba, ko, right? And the idea that they would then test to see whether the infant could parse it into, or whether the infant would show a familiarity bias for things that had higher transitional probabilities over things that had lower transitional probabilities, right? And you can do careful matching to actually do it as conditional probabilities rather than the point is, given this undifferentiated stream of syllables, infants show pretty good evidence of having recovered the word boundaries that structure that input, right? So that seems important, and I can't believe no one has ever followed up on it, haha. Right? Because that unleashed a whole series of experiments where, in fact, people would then try to use SRNs to show, look, this is just like what the SRN is doing, and then people would, famously Gary Marcus would come up with sorts of versions of this problem that the SRN couldn't solve, and then there were arguments about what the format of representations needed to be and how general they needed to be, and really what was going on with the learning. But it's pretty widely accepted even by even by people who think that there's a lot more to language than just learning patterns of statistics, like myself included, that something like this is going on. Okay. So there's a fly in the ointment here, which is that if you want to model, right, this phenomenon or any phenomenon of this kind, you have to assume a format for X. Right? So if you, so I'll just clarify that on the next slide. So, all the models in demonstration statistical learning, as far as we know so far, are what I'll call identify first models, right? So they assume first that learning occurs, the learning mechanism is sort of fixed at which unit the statistics are calculated over. This is less of a problem in SRNs because they maintain their context, but you're still predicting, okay, here was syllable X, now I predict the next syllable, right? And that the units are delivered to the learning mechanism in something like discrete form, right? So I'm learning about sequences of things. Okay, what are the things that I'm learning sequences of, right? How do I, right? So if these two assumptions don't hold, it doesn't really make any sense to talk about predicting X at P from all prior X, or learning words based on the probability of P given ba, right? Like I don't have a marker, it's okay. So if I'm not sure I heard P, right? Or if I'm not sure I heard, I'm not bounced, right? So, I mean, right? So if I'm not, if I'm not sure I heard ba, right? And I've got probability of P given, I don't know, something, right? Like how do I compute this, right? If there's ambiguity here, do I just explode this out over all the possible things that I might have heard? Do I allow that to be vague somehow? We don't have very good ways of thinking about that. Even though we know, right? First of all, we know that speech is inherently ambiguous, especially conversational speech or the naturally produced speech. So we know that you don't veridically identify ba as it's coming in every time you hear it. Part of identifying ba is the prior context in the first place, and so you have this sort of chicken and egg problem of well, if the context is made up of syllables and the syllables are helping me, if I can only identify the syllables from the context and the context is made up of syllables, how do I solve that kind of constraint satisfaction problem? And how do I do it under circumstances like this where I really don't have any additional cues to where boundaries are, right? So there's a problem of, assuming in the practical case that infants, for example, are able to recognize syllables with 100% accuracy at 3 hertz. Probably they can't. But it also doesn't really fit with the radical spirit of the proposal, right? The idea is that they get all statistics all the way down. It's you just have these multiple levels, and you learn the language from calculating statistics over these levels, and it starts to look very much like a an ancien regime kind of hierarchy here, where you have features, and then you compute higher order features from those features, and then you compute segments from those features, and then and then you look up the words from those segments, right? This is a very useful descriptive model for what the sort of levels of description of language might be like, but it sort of lost its luster as an explanatory framework. So here's a snarky experiment to get at this. Do you want this back? Yeah, I might hurt somebody if I tried to get it back. So here's a snarky experiment that we can do. We can ask, do people learn in the Saffron task despite being able to identify syllables? Okay. So what we're going to do is give people a familiarization stream. I'll show you what it sounds like. Produced by a pretty crappy speech synthesizer, this Imbrola synthesizer, which I'm not sure some of you, I see nodding, yeah, so it's not good. But it's been used in these studies. And so we're gonna see whether people can discriminate words from part words, that is, strings of stimuli where the transitional probability is perfect versus strings of stimuli where the transitional probability is not perfect, but they're items that you've heard before. And then we're going to ask people to demonstrate that they can understand the synthesizer more or less, right? So they're going to transcribe single monosyllabic words produced by the same synthesizer. So medium frequency English words, relatively familiar, monosyllabic words, played one at a time. The participant presses a button to initiate the playing of the sound, so they have every opportunity to understand what's being said, and they type in what they think they heard. And then just for giggles, we do task one again to see maybe, like Howard Nussbaum has done some really nice work showing that you can learn a lot about a crappy synthesizer by doing a word recognition task with it. So maybe learning the synthesizer will change the performance somehow. Okay. So here's what the test stimuli are like, or here's what the familiarization stream is like. All right, so. So, I mean, it's not like a complete mess. Like you can get, there's a pa in there probably, and a te, or maybe a t, or maybe it's a pay, or right? So there's a ton of ambiguity, yeah.
Is that what Saffron's stimulated?
Saffron used the 96 paper used like the Macintosh synthesizer, which was not so different from this. In later studies, they got really careful about splicing, like cross-splicing recordings of naturally produced speech. So it's heavily sort of massaged, but natural speech, and that, I mean, it sounds much, I mean, it's much easier to understand, but, they get the original study was with a synthesizer, like, I mean, not so different from this. The Macintosh synthesizer might have been a little bit better. But, we didn't, I mean, we did the experiment, right? So we asked people, how familiar was, say, pa-biku versus biku pa, right? So pa-biku is a word, like b given pa is perfectly predictable, and ku given b is perfectly predictable. Whereas if you do biku pa, well, pa given ku only has a probability of about 50%. And so that's what's intended here by word versus part word. So real words, like words that were used to structure the familiarization stream, are highly discriminable from part words in terms of their familiarity. Oh, sorry, this is an accuracy test. So we asked people, did you hear the sequence before? And words are preferred over part words, and part words are also preferred over non-words, right? So non-words are strings that didn't occur at all in the familiarization stream, whereas the part words did. They're just less perfect, and in fact, like, people have a bias. They will say that they know that they heard the part words, whereas they didn't hear the non-words. Okay, so it's natural to assume that what's being learned here amounts to transitional probabilities computed over syllables, because that's what we gave people, right? I mean, if you don't, if I hadn't played you what the syllables sound like, you'd be like, oh yeah, they played syllables. Those are English syllables. People can recognize those, right? When you actually listen to what the stimuli sound like, probably not so good at recognizing them. And in fact, accuracy for like monomorphemic, monosyllabic word recognition is about 30% in the first half of the stimuli. That's way, way better than chance because it's any monosyllabic word they can write down, right? And not only is accuracy quite poor, but further evidence that they're sort of still trying to absorb or they're still absorbing information about how the synthesizer is structured. The second half of the experiment, performance is much, much better. So these are confidence intervals. So there's a very large and significant difference in accuracy between the first and second half of the transcription experiment. Okay. So what happens when you then re-expose people to this familiarization stream and ask them to do a part word judgment? Pretty much nothing. Right? So they have the same, their performance does not change as a result of greater experience with the synthesizer. So, some preliminary conclusions there. Well, under listening conditions where people fail to identify familiar monosyllabic words, they can still learn from transitional probabilities that defined over nonsense syllables. So it doesn't seem very likely that they learn by first identifying the syllables and then computing the likelihood of the next syllable given the prior syllable, because they can't identify syllables even when they're real English words, right? So it just dramatizes the problem that we're about to talk about. So what's the alternative to this? Well, it's sort of present in the sort of SRN framework, right? So if you think about the sort of famous finding structure and time demonstration with individual words, you have these sort of telegraphic sentences like boy chases boy, or boy sees boy, right? Or boy walks. And note, and this is just a similarity space that's defined by the hidden layer in the SRN, right? So note that different instances of the word boy occur in different locations in this space, right? Because what's important for defining sort of, the model's internal representations is not like the local representation of this particular word, but of the sort of state of the network, right? So you can think of this similarity space as being sort of, a similarity space in the state of the network. And so when you get to the object, if you have boy as the object of the sentence, it ends up landing in the same place, whereas when the boy is the subject or what have you, it ends up in different places, right? So we tried to create a situation where we can make this really, really literal, right? Where we generate stimuli that have an organization in a similarity space, and we ask people to learn not sequences defined by probabilities of the next syllable given the current syllable, but we'd ask people to learn about trajectories through a similarity space. So the first crack we took at this was finally, after much trauma, published in 2013. It's a study that we did with using stimuli from Wade and Holt. It's a fairly complicated experiment for a number of reasons, but the TLDR version is that we would give people these non-speech stimuli that naturally, they don't have ad hoc, they don't have pre-existing categories for them, and they don't have labels for them, but they have a particular organization in similarity space. So you have these two red conditions that are easily discriminable from one another, and these two green conditions that are sort of all stuck together in one corner. And even though we defined the experimental manipulation over these four categories, people behaved as if there were only three categories of stimuli. Right? So people would learn transitional probabilities in such a way, and I don't want to rehearse all of the tests that we did to demonstrate this, but they basically they would learn as if there were only three categories of stimuli. Right? A lot of that has to do with the lumpiness of this H1, H2 part of the similarity space. That is, we wanted people to learn that H1 and H2 had different functional roles or were different, in different positions in the sequence, but they're interdigitated in this similarity space, right? So you have a couple of things operating at cross purposes to one another. So we stole another set of stimuli from Laurie Holt because, among other things, she makes amazing stimuli. So we borrowed this 2D auditory space from a paper that she did with Andrew Lotto, who also makes amazing stimuli in his own right. Yeah.
Sorry, just a quick question about the prior slide. Okay. Similarity space being across phonetic features, or
no? These are. I should have said more about these. These are the Space Invaders sounds that they use. So they're filled with square waves, and they have those are sort of formant-like structures that they have. And what makes the H stimuli, that's just for hard, what makes the hard stimuli hard to discriminate from one another is that they're defined by the onset of what looks like the second formant there. And so the easy stimuli sound like, or like, right? And so they're relatively easy to discriminate from one another, whereas these have, I can't even do the H1 stimuli, they have transitions to them. They're more like, ow. And they're sort of overlapping, right, in that similarity space. So that similarity space is derived by it's literally an MTS done on pairwise similarity judgments by the participants in the experiment.
All right. Thank you.
Okay.
So you know that H1 and H2 aren't discriminable in some other dimension beyond the two there.
That's all there. I mean. Yeah, well, so they are discriminable. So naively, people don't discriminate them. We use these stimuli because Laurie successfully taught people. I made reference to this Space Invaders thing. So she has a Space Invaders game essentially, and you play this for half an hour. And if the aliens coming out of the top left corner are producing this sound, and the aliens coming out of the top right corner are producing this sound, after half an hour of playing this game, you're able to discriminate those sounds from one another, right? So that was sort of what, to unpack a little bit what's going on here. I was like, well, so you can learn it in this perception for action context. What if you just have a sequence of these sounds, right? Will you learn, that was the motivation for this experiment, was would you learn these categories given a stream where they're organized as bigrams, and if you catch on to that, then you learn that they're in different distributions. And it turns out you just don't, right? Okay, so we took another set of stimuli. They vary in, so on this axis, they vary in frequency modulation. So you can see that there's a low modulation frequency here, and there's a high modulation frequency there. So that just means that they go up and down by 50 hertz, and the rate at which they go up and down by 50 hertz ranges from 35 to 197 hertz, right? So there's more chirpy stimuli at the low end and more buzzy stimuli at the high end. We also vary the carrier frequency from 690 to 960 hertz. So, sort of high pitch sounds. You'll hear them in a moment. Critically, the modulation frequency and carrier frequency sort of merge to form a pitch percept. So you don't really hear these dimensions as totally independent. But even more critically, first of all, Laurie and Andrew had done some norming. Like, these numbers were not just picked out of thin air. They're basically just noticeable differences on each dimension, or they're equally spaced on each dimension. And we did some match to sample testing to suggest that locations, so each step, if you move in one perceptual step, you're moving really you're moving in one step in perceptual space. So if you move, diagonally through this space, one position, that is perceived as the same difference, right? So it's really a uniform perceptual space. Here's what the corners sound like. All right, that's this one. Right, that's up in the top, so it's chirpy to buzzy. I'll do that again. Right, and then the carrier frequency goes up, and then the, right? So just see. Okay, so you listen to sequences like that, it's terrible. I'm sorry, I apologize to the people who run these experiments, right? You just listen to like for about 10 minutes. We let you read something. We don't police too much whether they have their phones or not. They're just letting this familiarization stream sort of wash over them. Okay, so that's the basis for all of the experiments that I'm going to show you. And what I'm going to talk about now is how we proceed from from a version of this experiment that's much closer, that's more or less like you can learn you can treat these corners, right? The corners are highly discriminable from one another, and so you can treat these corners as sort of symbolically, you can come up with ad hoc labels to them and learn transitional probabilities using those ad hoc labels. And then I'm going to make the space messier and messier until like we can show that you are no longer using those ad hoc labels, but instead you have to track the changes over time as trajectories through similarity space. Okay. So now let's just take the four corners of this space, right? So carrier frequency on the y-axis and modulation frequency on the x-axis, and this is just the four sounds that you've heard. And we make a sequence by having AB, and CD as bigrams, right? So you can go from A to B, you can go from B back to A, or you can go from B to C. You can go from C to D. If you're at C, you have to go to D, and if you're at D, you can go back up to C, or you can go over to A, right? So this is like the case where, given a ba, you predicted P, right? So given an A, you have to predict that you're going to hear a B because you've only ever heard B after A. When you hear a B, you have some ambiguity in the prediction. Right? And then we developed four different types of familiarization testing stimuli. So the equivalent of words in the Safran et al. Paradigm is A, like starting with A and then moving on to B, or starting with C and then moving on to D. The equivalent of part words, right? So given A, you're 100% likely to go to B, so those are the most predictable sequences, right? Given B, you might go to A, right? You might go to C. So if you just reverse that A-B sequence, then you have a sort of part word type condition where it's something that you've had some experience with, something that you've been exposed to, but it's not the most predictable sequence, right? Then we can make non-word stimuli where you go from A to D. You just never do that in the experiment. And then for comparison with later experiments, we repeat stimuli in the A category. All right, and we ask people to rate the stimuli on how familiar they are. We just say, do you think you heard the sequence? 5 is definitely not, so I'm sorry. I'm going to talk about high familiarity things as being lower on the y-axis. I really ought to fix that. But so these ones, it's like the NIH scoring system for those of you right? So these ones down here are really good, right? So these are things that people say that they definitely heard, right? So if we give them, if we train them on A, B, C, D, A, B, A, B, C, D, C, D, A, B, A, B, right? They're like, they hear A, then they hear B, they're pretty sure they've heard that. The part words and non-words are sort of equally bad relative to the real words, which is a little bit unexpected, right? The part you should be a little bit better at. You should be a bit more familiar with the part words than the non-words. So maybe a little bit of a divergence from the typical statistical learning findings. And category 4, where the stimulus is repeated, right, is really way worse than the other categories, right? So we can see people responding, definitely not, right, or somewhere in the 4 to 5 range for those stimuli, right? And this is just a jittered scatter plot of all of the subject units for all of the conditions, so you can just see what all the data look like. Okay. So now we can add a small amount of variability, and we can test for effects that are sort of similar to what was found in Emerson et al., right? So, but without the lumpiness, right? Because those stimuli we just sort of took from, well, these stimuli we also just took from an existing experiment and just chose more carefully. But we just sort of plucked those stimuli out, and they turned out to have this sort of weird distribution. So now we have, 4 A's, 4 B's, 4 C's, and 4 D's, okay? And we present people with a familiarization stream where they hear every possible pairing of A and B, right? So all 4 of those A's co-occur with all 4 of these B's, and they also hear all possible B's with all the A's and C's. Okay? And same thing all the way through. So they still have a sparse, so we've introduced a little bit of variability, but there's still a very, very sparse distribution in the similarity space, and it's still sort of possible to break the space up into these categories because the A's, B's, C's, and D's are all highly discriminable from one another. So here's what the familiarity test includes. It includes real words, it includes part words going back in the opposite direction. And now, because we have multiple stimuli in each of these quadrants, right, we can have 2 repeat conditions, right? So we can have a repeat condition where you start in A and you end up in A, but you sort of go in a plausible direction, right? And we have another condition where you start at a low A and go up to a high A, or you start at a low B and go, so you're going in sort of the opposite direction than you ought to, right? This assumes that you have high enough resolution in your perception of these categories to distinguish these from one another, which may or may not be the case. All right. So condition 1 is a word. Condition 2 is the part word, perfectly analogous to the first experiment. Condition 3 is repeating, going in a plausible direction that is moving in from the corners. Condition 4 is repeating but going in the opposite direction, going out from the middle. Yeah.
Sorry, just use the word plausible. What makes that plausible as opposed to implausible?
So you start at A. When you start at A, you go down to B.
Oh, okay.
Right. So you're thinking about the. Right. It's a switch from thinking about it as a sequence from this corner to this corner as the trajectory that you're following in terms of the angle of movement, right? And that's going to get. This experiment is sort of doesn't. This experiment is more of a sort of, well, this experiment didn't really work out the way we thought it might. But that concept that like plausibility is determined by the angle of movement is going to be really important for understanding the next experiment. So thank you for asking that. Okay, so under these circumstances, you get this classic word versus part word difference, right? So the one stimuli are rated as, definitely or almost definitely you heard them. The part words now sort of pull apart from these other non-word conditions, which we expect because those non-word conditions are repeated, right? And those 2 non-word conditions are sort of equally bad, right? So we're still in the domain where you can separate these corners out from one another, right? And you can just go ahead and label those corners, right, as A, B, C, and D. And you can explain all the results by saying, well, I've heard A, B's, I've heard B, A's, I've never heard an AA, right? And so these 2 conditions are equally poor. Okay. And just a side note, like, if you look at these experiments side by side, you can see, even though it was not a tremendous amount of variability, we only had, we had 4 stimuli in the first experiment, we had 16 stimuli in the second experiment. The spread of scores changes fairly dramatically. People have this bias to just sort of treat everything as more familiar when they're less certain what's going on, right? And so we haven't tested for this, but it may have something interesting to tell us about stimulus variability and participants' confidence in their familiarity ratings. That is, so if you literally repeat the same stimulus over and over again, you have greater sort of confidence in the word part, even the word part-word contrast than you do. You have a greater confidence in the word part-word contrast than you do when you introduce variability. So that's just something to throw out there. Okay, so now finally, I can tell you about the study that we wanted to do in the first place. So instead of just the corners of the space, right, we now present you with all of the stimuli over the entire space. So there are now 64 different locations that you can visit in this two-dimensional arrangement. And people are familiarized with sequences, like all of the A's followed by all of the B's, all of the C's followed by all of the D's. And this is the part that I had to redo after after making some plots and realizing, to my horror, that you need a recursive algorithm to make sure that you evenly cover the A and B space, or the A and C space, given all of the B's. And it was just, it made my head explode. So don't worry about it now. But basically, you'll see some plots of what those trajectories look like. So here's what a trip through the space looks like. You start with C, and then you get a D, and then maybe you get another C, and then maybe you get another D, and then, well, you'd have to get another D after C, right? Because those are the rules. Right now, we're all familiar with this, right? And then you get a D, and you can either go back up to C or go over to A, etc. Right? So imagine this kind of trip through this similarity space, or these trajectories through the similarity space, but as just a sequence of sounds. So these like CF, MF space. All right. And so we're going to see now, like under these circumstances, where like this. I mean, this experiment was designed. I mean, if you think about the fact that the space is perfectly uniform and that the trajectories are aligned in such a way that you're equally likely to visit any location down here, given any location up there, right? It should frustrate any sort of category learning approach, right? You probably won't get very far trying to learn that there's a C quadrant and a D quadrant and an A quadrant and a B quadrant at the same time as you're trying to track these locations through space. But you could, right? I mean, that's like if you just draw this line, right, and say, these are the A's, these are the B's, these are the C's, these are the D's, you absolutely can compute that, right? You can compute these statistics, like the probability of B given A, or the probability of D given C. All right, so we can generate. So we can generate sort of a set of test stimuli that allow us to compare predictions generated by an identify first model and predictions generated by a model that says, you don't much like label these things and then predict the next location given the label of the current location. What you do is, given a location in space, you have a rough idea of the possible angles that you can move in, and you are computing like how likely am I to go in any of these angles, right? So you can see what I was describing before. Maybe I struggled with how to visualize this, so maybe I hope this is helping, right? Like you can see, given any point, each point in A, right, has a relatively restricted range of angles that you can trace out given your position in that location, right? So if you're all the way up in that corner, you have a sort of restricted range because you're only going to come down to this position 1, 4 down here, right? Now you're in B, right? And you have a much wider range of angles that you can take because you can either go back up to A or you can go over to C. Right? So is this what we're learning? Are we learning that given these positions in space, we have a restricted set of angles that we can follow, or are we learning to carve the space up into 4 chunks and predict which chunk we're going to end up in given the current chunk? Excuse me. So here are the kinds of stimuli that we use to test that. And so I'm going to keep, and again, you know, I appreciate feedback on whether it's helping or hurting to have this sort of grayscale back here, right? We have test conditions that are designed to sort of pit these things against one another, right? So these are the words, right? These are the word-like stimuli, and you can see we start at an intermediate location in quadrant A, and then we follow the median trajectory, right? And we follow it 3 units into the middle of quadrant B, right? And you'll notice that the points that we terminate at are not points that were in the familiarization stream, because it's a continuous space. So we just follow that angle and then compute. You know, it's not. They happen not to land on integers. So we go from, you know, 2, 6 to somewhere around 3, 3, but not exactly. Because if we assume that people are treating the space as continuous, it shouldn't matter that you've heard this particular sound. It should matter that you're in that general location in the space. So we can make part word stimuli in the upper right-hand corner there, right? You start in locations in quadrants B and D, and you follow the most likely trajectory. And notice the angles of those trajectories are different because there's regression to the mean, right? So you're likely to go, you're as likely to go back up to A as you are to go back over to C from B, and so you know, so those are at a much more acute angle. And then critically, we can make 2 different repeat conditions, right? One where you start all the way up in the corner and then go in basically the right direction, but terminate in the same quadrant, right? So if you're just keeping track of what quadrant you're in and labeling that, then this is an AA, this is a BB, this is a CC, this is a DD. They should be terrible because you've never heard AAs, BBs, CCs, DDs. Right? And then if you're learning about the trajectories, they should be pretty good, right? Because you've gone, given that you started up there, going in that direction is fine, right? You just happen not to make it all the way into the next quadrant. And then we can contrast that with a situation where you start down here, right? You start at the ending location for the 3rd category, and you go backwards, right? So these are AAs, but these are going in the right direction, and these are going in the wrong direction. I think I just said all of this. Yeah, right, okay. And yeah, this is the problem with giving a talk for the first time in front of a live audience, right? But yeah, go ahead.
Sorry to keep asking questions, but
no, it's great.
The question that I have is: were participants in the they were exposed to words, right? And by words, I mean the
A B C D A B A B A B C D C D A B A B.
Yeah. So then my question is, what's their basis for the BB trajectory there? Because in that lower left-hand corner, haven't all the transitions always been from top to bottom, so to speak?
No, if you start here, right? So these are the angles. I don't know if you can see the grayscale, right? But those are the angles that are sort of that have been traversed, right? So if you're starting down here, right? Well, you can go up. You can go at about a 45-degree angle, or you can take on any angle in between.
Okay, so they were exposed to transitions in that direction.
Yeah, because it's A, B, C, D, right? So if you're in B, you can either go back up to A, or you can go over to C.
Or you can start the next word. Okay.
Yep. I see. Yep. That's how. But it's like weird, right? I mean, that's how these things are supposed to work, right? Mm-hmm. So you have pabiku, and so then bikupa occurs because you get pabiku. Mm-hmm. But sometimes, you know, you get pabiku go tiru, so you get keep. Sorry. I always forget what syllables I'm using. Whatever, you get the other transition. You get the transition from the other word. So if you mix words together, then you have a sort of trough of probability there, and that's just what's going on here. Instead of a trough, you have just a wider fan of angles that you can take on.
Okay, I see.
Right at those, so you can go to BA or BC. Okay. Right? So I hope you can see that a comparison between these 2 kinds of non-words is critical, right? If you're, so as I just described, like this is a legal direction that you can take, this is a legal direction that you can take, these are going in the wrong way, right? So, but if you collapse over this whole quadrant, they're equivalent categories. So what happens? Right? And just to orient you to the labels for the next slide, because I don't know. I mean, I've been working on this for a year and a half, and I feel like I can almost explain it. So, so category 1 is the word type situation, right? Category 2 is the part word situation, and then these are 2 repeat situations. This repeat situation is felicitous on the trajectory learning model, and this is infelicitous. All right, when we finally look at the data, the only condition that's different from the other conditions is condition 4. Right? So you don't really treat words as different from part words. You don't really treat the part words as different from repeated items, but you really don't like the items that start in a quadrant and then go in the wrong direction given where you started out. Right? Suggesting that like what people are learning here is not, they're not learning this by collapsing the quadrants, right? Because there's no evidence for any of the typical statistical learning type phenomena necessarily, but there is evidence for learning about these trajectory differences. Okay, so, and again, actually these stimuli are all rated as less familiar than the prior 2 experiments, and there's definitely something to say about variability and how familiar people perceive the stimuli to be. There's also, I'm going to talk in a second about well, is there evidence that there are multiple learning mechanisms at work here, and is what's happening in this experiment just a different mechanism from what we see, or should we expect to be able to explain all of these experiments in this alternative framework? Right. So some constraints based on data that I haven't shown you because we're not finished with it yet. First of all, the general conclusion that I'm going to leave you with, and I'll emphasize this in a bit, is that people really can learn trajectories through similarity space under the right conditions. And so the concerns now are what are the right conditions, right? So does it matter, for example, that in these experiments, everything is going up, down, up, down, up, down, up, down. Right? You get A, you get B, you get C, you get D, you get A, you get B, you get A, you get B, you get, right? So you're always going up and down. And so we can test that by making the trajectories A, B, D, C, right? So if you're up in the left-hand corner, you can come down. If you're up in the right-hand corner, well, it's ambiguous where you're going to go because that's the end of a word, right? If you're down in the right-hand corner, you have to go back up. So we can make stimuli we can make sequences that don't have that overarching sort of pattern to them, and they're harder to learn, but people learn them. Right? So we basically replicate these effects with a smaller effect size. What if you taught people to categorize these stimuli, right? Well, so here's what some stimuli that you sort of have exposure to, they sort of sit in a similarity space, and you give people disconnected labels to them. This is from Gary Lipkin, some computational models, but it's a nice illustration of what categorization might look like. If you give people consistent labels, right, and you give them feedback, they can pull these things apart, right? So we have this uniform distribution of stimuli, and we've done everything we can to discourage people from clustering them somehow. If you gave people the right kind of experience, they might cluster them together, and that might change the way they're representing the similarity space. And in fact, it increases the effect size, right? Which leads to another question is well, is it the fact that you sort of implicitly gave people labels so now they can do this other learning thing? Or is it that you've warped the similarity space by training them on categorization? And so that's something that bears further work. Okay. So just as a very general conclusion, contrary to popular belief, there's still interesting work to do, I think, about how people learn from statistical irregularities and sequences, right? We've been in sort of statistical learning winter for a couple of years maybe, and so, I don't know. This is like the deep learning of statistical learning. That doesn't even make any sense, I'm sorry. So under some circumstances, identify first models can't really obtain because people demonstrably fail to identify the intended units. So that was the initial demonstration that I showed you. But we can conceive of sequence learning as learning about trajectories through a similarity space, And at least the last experiment and some of the stuff that I told you about suggests that that's a reasonable avenue to pursue. And it might be possible to show that prior evidence for tracking of transition probabilities actually due to this sort of trajectory through space phenomenon that we haven't named yet, right? So the way you do that is like put the syllables into a sort of similarity space based on, you know, some combination of phonetic and maybe acoustic features, and then make predictions based on trajectories through that multidimensional space rather than like as unit values, right? The probability of this symbol given that symbol. No, it's the probability of like this general area over here where pa, ma, and pa and ba all sit together to this other space over here, right? And so a formal model is really needed, and we have some ideas about what to do with that. And there's actually a math major who wants to do some things combining graph theory and sort of topographic representations that I can try to talk more about, but I'm happy to stop here for a variety of reasons. So thank you, and thank you. That's my lab.